Welcome back. Over the last couple of classes, we have been talking about drawing shear, force, and bending moment diagrams. Let me do a really quick recap of that one more time. If I have a beam and it has a bunch of things acting on it, point forces, maybe distributed loads. If I want to find where are the shear force and bending moment maximum, because I want to try to design this beam and make sure that it's not going to fail given all the loads acting on it, my first step is always going to be a whole free body diagram. That whole free body diagram is going to let us find the reaction forces over here at the wall. If we call this point A, it'll let us find AX, AY, and the reaction moment at point A. Those are found by writing the equilibrium equations. The whole goal is to find the support reactions. Once that's done, we need to figure out how big the internal loads are in order to figure out how big the stress is at a given location. So one option is to just go take cuts at specific locations in order to find the internal loads, which for a beam would be, in general, you could have a normal force, but what we're going to care about more are shear force and bending moment. But that would only give it to you at a specific spot. Let's say we wanted to find it right here at this location. Well, we would take that cut and we would need to draw a free body diagram that shows our internal normal force, our internal shear force, and our internal bending moment that we want to solve for. And we would need to then draw on there all of the other applied loads. We would then use equilibrium equations again. And if we want to find the internal load somewhere else, we would take a cut somewhere else, like at that red location. And we would draw a different free body diagram that would have a different amount of loading on it. And so it would end up with different internal shear force and bending moment and potentially normal force. Once we have all of these, we could then some force in the y direction and some of the moment about each cut, set those equal to 0, and we would eventually be able to solve for v as a function of x and m as a function of x. If you ever do take a cut in the middle of a distributed load, like I did for this red one right here, you want to make sure that once you cut that beam, you only keep the part of the distributed load that's actually on the part of the beam. Only keep the part of the distributed load that acts on your cut piece. So up here, we did the whole free body diagram, we would have found the area under the whole distributed load and replaced it with a force that acts at the middle of that rectangle. But down here, since we're cutting partway through, we only take the area under this part of the distributed load, find a new equivalent force, put it exactly at the middle of that little rectangle. All right, so we could do this, but it's typically kind of slow. So we spent the last couple of classes trying to figure out how to sketch fairly quickly the whole shear force and bending moment diagram. Well, for this simply supported beam here on the left, you would want to first do a free body diagram to find your reaction forces. But since it's completely symmetric, it turns out we're going to end up with just F over 2 on each end to balance it out. So our shear force diagram is going to first start up here at F over 2. And then it's going to go with a 0 slope because there is no distributed loading. Then it's going to jump down by F, which will make it end up at minus F over 2. And then again, no slope because there's no distributed loading. And finally, at the end, it would have another reaction force of F over 2. So our shear force diagram ends up looking like that. To get our bending moment diagram, we have no applied couples at the beginning or the end. And what's going to happen is for this first half of the beam, we're going to have a positive slope of F over 2. Constant positive slope means straight line that goes uphill with a slope of F over 2. And then we'll have a constant downward slope, also F over 2, or minus F over 2. If we want to figure out how high we get, that is actually the most important number for what we're starting today with bending stress. We need to know how big is that max bending moment. We can find that by shading in one of these rectangles. Area of a rectangle is going to be F over 2 times L over 2. It looks like it's going to be FL over 4. That's going to tell you what this peak is. It's going to be FL over 4. And that's what we need to know from that first one. So if I were designing this beam and I want to make sure it doesn't fail because of too big of a bending moment, this is the value I want. The maximum bending moment right there. It's going to be at the middle is where you'd expect this beam to break. And what you want to design to is this bending moment. Let's look at our distributed loading case. Once again, we have a shear force diagram. What's going to happen is the total force here is going to be whatever your distributed load is over the length. Let's say that it's still F. The total force is F. So we're still going to have upward on each end F over 2. So we start at F over 2. And now what's going to happen is we have a constant downward slope of W And at the end of the beam, we should end up down at minus F over 2, and we're going to come right back up. And F, in this case, would be equal to W times L, if L is the length of my beam. And so my shear force diagram looks like that. So now my bending moment diagram is going to look a little different. It still has to start and end at 0 because we have no applied couples and no fixed supports with reaction couples. We don't have any couples on the ends. What's going to happen is we're going to start with a big positive slope, eventually in the middle get to a 0 slope, and then end up with a big negative slope. So this is going to be a concave down parabola. And the peak will be right at the middle of the beam. And to figure out how high that peak is going to be, I need to find the area under this triangle. Area would be 1/2. One of the sides is F over 2, the other one is L over 2. So I'm going to end up with a peak M of FL over 8. And right there is what you want to design to. So it actually makes a big difference to the beam whether the force is applied as a point load in the middle or a distributed loading across it. And a really quick VM diagram curve will give us the information we want, which is what is the max bending moment that we're going to design to. Today, we want to take those bending moments and use them to find stress. And I actually first want to remind you what we did with axial loads and torsion. With axial loads, we had a bar, and to the end of the bar, on each end, we had a normal force, and that led to something called normal stress. And the magnitude of it was just that normal force divided by the area it acts over, where the area would be that right there. And we argued that as long as you're not really close to a point load application, say you're back here somewhere, that normal stress is going to be totally uniform all over the cross section. The other stress we've already learned about is the stress coming from torsion. With torsion, we had a bar that might be subjected to a torque T, and our equation was torsion gives rise to not a normal stress, but a shear stress, and it's going to be T rho over J, where rho tells you how far out from the middle you are. And if we want to look at how that stress is distributed over the area, what is that going to look like? It's going to change direction as we go around the outer edge, and it's going to get smaller as we move in concentric circles until it's 0 at the middle. So this has a very non-uniform distribution. You might want to remind yourself that this is max at the outer radius, 0 at the middle, and it changes direction. Let's see how bending stress is similar or different. Bending stress comes from a bending moment. So if I have a chunk of material that's subjected to a bending moment, if this were a really squishable material and you could see this visually, what's going to happen is it's going to bend. And what I've drawn here is a positive bending moment. And the reason we know it's a positive bending moment is because it ended up curved into a concave up shape. So here is the deflection you get from a positive bending moment. You want to think of this as a couple. We don't always remember that from statics, but it can be really helpful with this. How do you get a bending moment like this? When we draw a couple like this, it was not created by a single force, it was created by a pair of equal and opposite forces, such as that. On the other end, we have another couple created by a pair of equal and opposite forces, and it has to be like this with the arrow to the right above the arrow to the left because it has to create the same clockwise moment on that end and the same counterclockwise moment on that end to be equivalent. So at the top of your part, you see how we have these two arrows pointing toward each other? That means at the top of the part, we're going to end up in compression. Those arrows are pushing in on the top. The bottom, we're going to end up in tension. And somewhere in between, we got to transition from compression to tension. So we're going to have something that's actually called the neutral surface or the neutral axis. Again, these are pairs of forces, call them F if you want, a distance D apart. That's what creates a couple. So anytime you want, you can replace a couple with a pair of forces the right distance apart. And in this case, it's just convenient to kind of visualize that the side of the beam that these little arrowheads are pointing on, that's where your compressive side is going to be. And the side that it's pulling away from, that's where your tensile side is going to be. So when we go and zoom in on just the side of the beam, right? Imagine cutting it right here and we zoom in. We're going to have compression at the top, tension at the bottom is what our stress needs to look like. And we have to have no stress somewhere in between because we have to go from tension to compression in a nice smooth pattern. This is also going to be a linear distribution. At the very top is where we get our max compression, if it's a positive bending moment. The very bottom is where we get our max tension. And at the middle, we have no stress. And this is called the neutral axis or neutral surface. I think I misspoke. I think I said at the very middle. At some place in between, we will have no stress. It may not be at the middle. It depends on what shape the cross section is. The neutral axis, just call NA for short, goes through the centroid of the cross section. Always. If this is my I-beam and the centroid is right in the middle, what I'm saying is I'm taking this two-dimensional side view and kind of rotating it so I can see the end. This right here, right down the middle, is my neutral axis. And that's kind of why it's called a neutral surface rather than a neutral axis sometimes, is it's really a whole plane that if you cut right through the centroid of the cross section. So there is my centroid. There is my neutral axis. And what I would have with a bending moment that went from bottom to top, up at the top, I would have compression all the way along here, tension all the way along there. Right at the middle is where the neutral axis is. So what if I have a non-symmetric cross section, like a T shape? Well, the centroid might be way up here. So right there is where that neutral axis will be. That means that the stress is 0 right there, and it's going to increase as you go away from there. If you turn that on the side and looked at it, your neutral axis is right up here. Your compressive stress that is not very far away from it, but your tensile stress at the bottom might be a really long way away from it. So can you see how when you have a non-symmetric cross section, you could end up with a really big stress at the bottom with a relatively small stress at the top? And that is because you actually have a ton of material up here to spread the stress out over, whereas down here you have very little material to spread the stress out. Sigma bottom, the magnitude of it will be much bigger than sigma top because it is much farther from the neutral axis, also located at the centroid. Okay, so what's our equation? Our equation is bending stress is a normal stress. Do you remember me saying tension and compression? Tension and compression are like this, tension and compression. It's a normal stress, but instead of uniform distribution, it is not uniform distribution. So our big equation of the day is normal stress is equal to, I like to write this equation with a plus or minus, my over I. Most books will either call it plus or minus, depending on what sign convention they are using. I prefer for you guys to actually just plug in how big is M, plug in how big is Y, plug in how big is I, and then actually look at the problem to figure out if it's going to be tension or compression. Every other approach I've ever tried with students tends to lead to lots of confusion. So just plug in magnitudes and then look at the problem to figure out tension or compression. So what are the things in this equation? M is the bending moment at that location. What is Y? Y is the vertical distance measured from the centroid. Remember, if you're at the centroid, you're on the neutral axis, the stress should be 0, and Y is 0 because you're no distance from the centroid. If you're a small distance from the centroid, you're going to have a small stress. If you're a big distance from the centroid, you're going to have a big stress. And then I is the moment of inertia. It's the area moment of inertia about the centroidal axis. That's really important. If you remember this from statics, if I had a cross section here, there's maybe my centroid. If I want to find the stress somewhere, Y is measured away from the centroid. And then I need the moment of inertia about this centroidal axis. Here is my centroidal axis. So you remember using the parallel axis theorem? I hope so. If not, go back and review it because you're going to need it. Remember, we can do table lookups to find the moment of inertia of these rectangles about their own centroidal axes. But then I need to use the parallel axis theorem to get them all collected about the same uniform centroidal axis of the whole shape. Let's do some examples. Here's my first example. It is a box beam, and we're actually asked to find M to cause the stress at point D to be 30 megapascals in compression. And you can see with the way that this bending moment is bending, D is up above, and that's where the arrowhead is, so that is going to be the compressive side. So let's write down our equation. Our equation says stress is equal to my over I. And let's get all the things that we need. For moment of inertia, don't know if you remember this trick, but if it's a hollow symmetric shape like this, the easy way to find the moment of inertia is to use the moment of inertia of the big box minus the moment of inertia of the little box. Moment of inertia of a square rectangle is 1/12. The base, what will the base be? I've got 150 plus 50, so 200 millimeters. And then the height, my axis I'm finding the moment of inertia about is this axis because it's the axis I'm bending about. So base is always parallel to the axis and the height is perpendicular. It happens to also be 200 millimeters. The height gets cubed, 1/12 BH cubed. That's for the big square. Now let's subtract from it 1/12, 150 millimeters times 150 millimeters cubed. And for now, we'll just leave it all in millimeters and then we'll convert it. So this comes out to be 91.146 times 10 to the 6th millimeters to the fourth. I like writing this as times 10 to the 6th because it makes the conversion to meters to the fourth really easy. It's just 91.146 times 10 to the minus 6th meters to the fourth. If you didn't have it as 10 to the 6th, so you could just swap 10 to the minus 6th, remember there are 1,000 millimeters in a meter. Since we've got to convert it 4 times because we've got it to the fourth power, you're going to need to divide by 1,000 4 times, which means whatever number this is, 10 to the 6th, subtract 12 from it. So we found I think we're pretty much ready to plug into our equation. Stress, we're told we want it to be 30 megapascals. Mega is times 10 to the 6th, and pascals is newtons per square meter on the left. On the right, we have m that we want to solve for. We need to know the y distance. Remember how we find y? Y is measured from the centroid of the whole shape to the point where we want to find the stress. So to get up to point D, we just have to do half of 150, which is 75 millimeters, or 0.075 meters. There's your y distance. And then we divide by moment of inertia. 91.146 times 10 to the minus 6th meters to the fourth. Solving, we get m. See how the units are going to work out. I've got meters squared here. If I bring this meters over, we'll have meters cubed. Then bring meters to the fourth to the top. 3 of those meters cancel, and we're going to end up with a number in Newton meters. I get 36.5 times 10 to the third Newton meters, but we can replace that with kilonewton meters. So that is 36.5 kilonewton meters. And there is our answer rounded to 3 sig figs. Why don't we go ahead and find the maximum stress? Remember where the maximum stress is going to happen? It's going to be the point that is the very farthest you can possibly get from the centroid. Since this centroid is at the middle, you can either go to the top or the bottom. It won't matter at all. At the top, it would be a compressive stress. At the bottom, it would be a tensile stress. So let's find the max stress. Max stress is usually more important anyway. Sigma max is going to be your moment, which we just found, 36.5 kilonewton meters, or times 10 to the third Newton meters, if you want everything in base SI units. The distance from the middle to the top or bottom is 100 millimeters, or 0.100 meters. And our moment of inertia is still 91.146 times 10 to the minus 6th meters to the fourth. And this comes out to be 40.0 times 10 to the 6th newtons per square meter. 10 to the 6th newtons per square meter is also a megapascal. So 40.0 megapascals is your max stress. It'll be compression on the top or tension on the bottom. For today, all we're going to do is have problems like this where we're given the cross section and we need to either find the moment, or we're given the moment, find the stress. Tomorrow, we're going to back up to the whole big picture, like a beam like this, and it's going to ask you find the maximum stress anywhere in the beam. You'll be able to do that. It just means you first need to draw your shear moment diagrams and figure out where is your max bending moment and how big is it, to then plug in and find the stress. So longer problem. For today, we're just zooming in on the cross sections. So here is my second example. It's a kind of complicated drawing, but it's got a bunch of A's in it, and A is just equal to 10 millimeters. So the entire width would be 8 times A, 80 millimeters, and the entire height looks like it's 50 millimeters. We're given M. We are asked to find the max tensile and compressive stress. So again, our main governing equation is stress is plus or minus my over I. Okay, I actually think the hardest part of this problem is finding the centroid in the moment of inertia. And I am a statics teacher, so I know it's hard. Let's just do it together and practice it. So first, let's find the centroid. I like to break things up into simple shapes, so I'm going to break this up into a rectangle with 2 rectangular legs on it. It kind of looks like a little table. Let me shade this one in green and shade the 2 legs into a different color. I don't know, pink maybe. I want to find that centroid. Now to find a centroid, you always want to have some kind of a reference axis. For example, the top will work just fine. What I need to do then is find the centroid of the green rectangle relative to the reference axis, and the centroid of the 2 pink rectangles relative to the reference axis. Then our equation from statics told us that y bar, the centroid location, is equal to the sum of the y tildes times their area divided by the sum of the areas. So I need to measure from my reference axis down to the green dot and then down to the two red dots, multiply each of those by their areas, and then divide by the total area. So for the green one, it's 10 millimeters tall, so the centroid will be in the middle, 5 millimeters down from the top. So y tilde is 5 millimeters. That gets multiplied by its area, which is 10 millimeters times, what was it, 80 millimeters, I think we figured out. While I'm there, in the bottom of the fraction, I'm also going to have the same area, 10 millimeters times 80 millimeters. Next, let's add to it. We've got two of these pink ones, so we'll just put a 2 out in front. And let's figure out where their centroids are going to be. Pink rectangles are 40 millimeters tall, so their middle will be 20 millimeters from the bottom or 20 millimeters from the top of the pink rectangle. But I need to measure it all the way up to my reference axis. So I got to go up 20 millimeters plus 10 more. So my y tilde is 30 millimeters. That number is the hard number to get. And now each of them are, it looks like 10 millimeters wide and 40 millimeters tall. So in the bottom of the fraction, I have that same area, 10 millimeters by 40 millimeters. Run that through the calculator and you get a number, which is 17.5 millimeters. So that is where the centroid of the whole shape is. Come down here, 17.5 millimeters. We're going to need that number later on. The other thing we're going to need is, it's really nice to also know how far is that from the bottom. So since the whole shape is 50 millimeters tall, we can figure that out by taking 50 minus 17.5, which I happen to know is 32.5 millimeters. So we're going to need to use both of those numbers at the end of the problem to find the stress at the top and the stress at the bottom, because we need to know how far we are from the centroid. All right, we got the centroid. Now the moment of inertia, the other pesky part of the problem. So reminding you that I for a rectangle, we used it above, but it is 1/12 BH cubed. So my moment of inertia, let's start with the green rectangle. 1/12, its base is 80 millimeters, and its height is 10 millimeters, which gets cubed. Now that is the moment of inertia of the green rectangle about its own centroid. I need to now use the parallel axis theorem to move it down to the centroid of the whole shape. So that is adding to it its area, 80 millimeters times 10 millimeters, and the distance between their two centroids. Distance between their two centroids, well, the centroid of the green rectangle is 5 millimeters down. Overall centroid is 17.5. We need to subtract them. 17.5 millimeters minus 5 millimeters, and that gets squared. So from your parallel axis theorem, here's the moment of inertia of the rectangle about its own centroidal axis, and then add to it its area times the distance squared between the two axes. The one axis goes through the green dot, the other axis goes through the black dot. Then we need to add to this our two pink rectangles. There are two of them, they're exactly the same, so we may as well save some time with the math. And I need to do 1/12. The base is 10 millimeters, and the height is 40 millimeters, which gets cubed. That'll give me their moments of inertia about their own centroidal axes. So I now need to add to them area, which is 10 times 40, and the distance squared. Again, I need the distance between the centroid of the pink rectangle and the centroid of the whole thing. There are a couple of ways to get it, but what I like to do is just use the same y tilde up here, which was 30. That tells me how far down this is from the top, and subtract from it the 17.5. So you can do this with 30 millimeters minus 17.5 millimeters, and it gets squared. So again, there is your area. There is your distance squared. Just a reminder in case you're really, really shaky on the parallel axis theorem. This uses the parallel axis theorem, which says that the moment of inertia about an overall centroidal axis, or any axis honestly, but we want this overall centroidal axis, will equal moment of inertia of about the rectangle's own centroid plus the area of that rectangle times distance squared. And this is the distance between the two axes. Okay, once upon a time you learned this in a statics class, and we just got to remember it and use it now. So when you do all of that math, you get that the moment of inertia is 0.3633 times 10 to the 6th millimeters to the fourth. Again, your calculator might not give it to you like that, but you can get it in 10 to the sixth, or just leave it however your calculator gives it to you. And then that becomes 0.3633 times 10 to the minus 6 meters to the fourth, which is a little more convenient to plug into the equation. Now we need to find those max stresses. Max tensile stress, and then we will do max compressive stress. Where will they be max? So let's go and see. The moment looks like this. So the moment was pushing in, the arrow was going in at the top. So it's going to be compression at the top and tension at the bottom. So compression at the top, tension at the bottom. Max tensile stress. The equation is my over I. It's going to be a positive because tension is positive. The moment was 75 Newton meters, I believe. Let me go double check that. Yes, 75 Newton meters all the way back there. Now, y needs to be the distance from the centroid of the shape to the place where you're finding the stress. Well, the stress is always biggest at the very, very top and the very, very bottom, because stress gets bigger and bigger and bigger as you go away. We're doing max tensile stress, which is at the bottom. To get to the bottom, we want to go from the centroid all the way down to the very bottom, where our stress is maximum. That distance is 32.5 millimeters. So plug in 0.0325 meters, and then the moment of inertia we just found, 0.3633 times 10 to the minus 6 meters to the fourth. We calculate it straight out of my calculator. I get 6.71 times 10 to the sixth newtons per square meter. That's a megapascal. So 6.71 megapascals, and it should be positive because it is tension. Max compressive stress will happen at the top. Same equation, my over I. This time I'm going to put a minus sign in front of it because compression should come out to be negative. Again, my moment is 75 Newton meters from a magnitude standpoint. Now my y, I need to go from the centroid to where it's max compression, which is up at the top. So that'll be 17.5 millimeters this time. 0.175 meters, same moment of inertia, and this one comes out to be minus 3.61 times 10 to the sixth newtons per square meter, or minus 3.61 megapascals. And the negative is there because it's compression. I didn't get the plus or minus here from the equation. I got the plus and minus from looking at the direction of m. And because m is squishing it at the top and pulling out on it at the bottom, think of this as happening because of a compressive force at the top and a tensile force at the bottom that creates this moment about the axis. So I'm going to have compression up here and tension down there, and that's where my signs came from. Sometimes these problems ask you to sketch the stress distribution on kind of a side view. So let me show you what one of those sketches would look like. From top to bottom, we had 17.5 millimeters down was our centroid. So that's where our stress is going to be 0. This is what the beam looks like in kind of a 3D perspective. When we do the cross section, we tend to look at this edge of it and just get the shape and put the shape here to find this. This sketch I'm doing is actually viewing it from the side. So it might be helpful if I kind of show a little bit of the side view. We had that 10 millimeter thing on the top with 40 millimeter legs, and our centroid was down 17.5 millimeters, and that is where the stress is 0. So if we go up to the top, we're going to get a compressive stress. You can draw that way if you like. And at the bottom, we will have a bigger, because it's farther, tensile stress. So at the top we have minus 3.61 megapascals, and at the bottom we have plus 6.71 megapascals. And if you wanted to know distances, this distance is that 32.5 millimeters, and this distance right here was the 17.5 millimeters to locate where the stress is 0. That's what a sketch would look like on kind of looking at it from the side. You've got your compressive stress at the top, your tensile stress at the bottom, and it goes through 0 at that centroid location, which is not in the middle for this particular problem. Hopefully this helps give you a good introduction to how to calculate bending stress. Important thing is you need the bending moment, you need the moment of inertia about an axis through the centroid, and you need to know how far you are from that centroid measured vertically on the cross section. If you come back for the next video, what we're going to do is start with whole beams, where we need to actually figure out the bending moment and where it's not given to us at the beginning of the problem. See you next time.